Good evening students. Let us start with the p-type extrinsic type semiconductors. Okay, we have already seen n-type semiconductors in which we had pentavalent impurity. So we have also seen what is doping. Doping is the addition of the impurities deliberately in a pure crystal in order to increase the conductivity, in order to enhance the conductivity. So if we add trivalent impurity to a crystal, the crystal so formed becomes the p-type semiconductor. The crystal so formed is the p-type semiconductor. So in this p-type semiconductor, we will be adding trivalent impurities. Trivalent impurities can be aluminium, boron, indium, any of the impurities having the valency 3, means in the outermost shell of that atom will be having 3 electrons only. So it will be having the valency 3. So let us start with the p-type semiconductor. Here I have shown a crystal having the impurity, trivalent impurity. I have taken your boron. You can take any example such as aluminium, indium, etc. So boron has having 3 valency, having 3 electrons in the outermost shell. So 3 of the electrons form the bond with the electrons of the germanium atom, and 3 of the electrons form the covalent bond, but one position is vacant over here, and that vacant position forms the vacancy, and that vacancy forms the hole, means it is the hole over there forming the hole, which is acting as a positive charge for the crystal, Now any of the electrons can jump to this hole and form the vacancy over there, Like suppose if these electrons want to jump to this hole, because it is acting as a positive charge, it can get attracted to this hole over here. So it can jump to that hole, forming a hole over here, and from where it leaves the electron, there it forms the hole on the other side. So this is another side over here. Suppose this type of electron, it wants to jump from here to here, and it jumps over here, it gets attracted to the hole, then it forms a hole over here, vacant space over here. Okay, so this type of crystal is having a majority of the holes. Only the electrons which are for the conduction are from the intrinsic type semiconductor, means at the room temperature itself, some of the not the room temperature, greater than the 0 Kelvin, at the temperature greater than the 0 Kelvin, some of the electrons will break the bond and they will move in the crystal. So those many electrons are just from the intrinsically type semiconductor, but rest of the majority over here are of the holes. So in this type of semiconductor, I am having NH is greater than Ne, means the hole concentration is greater than the electron concentration over here. Okay, so such type of crystal is known as p-type semiconductor. So the hole is formed, and some of the holes recombine with the electrons. Some of the bonds break over here, and the covalent bond breaks, and the electrons start moving in the crystal, and some of the electrons form the recombination. They get recombined with the holes, but still the holes, if we see the concentration of the holes is greater as compared to the n-type semiconductor. In the n-type semiconductor, the concentration of electrons was greater. In the p-type semiconductor, the concentration of the holes is greater. So mainly the conduction is through the holes over here. Okay, if we connect this crystal to the battery, the holes start moving to the negative charges, and the electrons will automatically move to the positive charges. Okay, so now let us see how the bands are formed in this crystal, valence band and the conduction band. And one more energy level is there, that is the acceptor energy level. Because there is a vacancy. This impurity is creates a vacancy over here. So this vacancy can accept electron, as I have shown over here. So this type of impurity is known as the acceptor impurity, and the energy level which it forms is the acceptor energy level. It forms the acceptor energy level. Okay, so let us see the formation of the valence bond and the conduction bond in this type of crystal. So over here the impurity is the acceptor impurity. Acceptor. It is the acceptor impurity. Okay, because it can accept the vacancy, can accept the electrons, and for the conduction it can accept the electrons. A hole is created, it can accept an electron. Okay, now let us draw the valence band and the conduction band. So this is my valence band, this is my conduction band. Okay, energy level, accepted energy level will be just above the, I should draw it straight, will be just above the valence band. Let us mark it as EA, accepted energy level. Okay, it will be from 0.01 to 0.05 electron volts. Okay, so the electrons from the valence band can jump to the acceptor energy level, thereby creating the holes in the valence band. So the majority will be more of the holes than that of the electrons. So the majority will be more of the holes than that of the electrons. And in the conduction band, the electrons are very less, because the electrons which are only available by breaking up of the bonds can jump to the conduction bands, but that are also very low. So the whole conduction is mainly through the holes over here. Because the electron can jump to the acceptor impurity. It can jump to the vacancy which is created, and it can create a hole thereby in its place, in its site. Like over here, it has created the hole in its place, and so we see that the holes formation is more, holes majority is more. So this was all about the p-type semiconductors. Now we will be starting about the p-n junction, then the p-n diodes, rectifiers, and so on. Okay, so please share my videos, please subscribe my channel. If you have any doubt, you can ask me in the comment section. Thank you.